Two main factors that affect pulmonary ventilation are going to be the lung compliance and the airway resistance. And so we'll speak about these individually, and then we'll go on to speak about how we can measure pulmonary ventilation based upon lung volumes, lung capacities, which are recorded using the pulmonary function tests. So basically, the compliance in the lung is pretty synonymous with what we've been describing in terms of compliance in other areas. So compliance in the veins as one main example. And so compliance is going to be the ease with which the lungs want to expand in order to accommodate airflow, okay? And so we've been speaking about the pressures that are required, the gradients that are required, the pressure gradients in order to move air, but we also want to think about the lung itself. Is it accommodating that movement of air, although we have a gradient? And so this is what we mean by compliance. And so the equation for compliance is the change in volume, in other words, how much air is coming in, divided by the change in the transpulmonary pressure. So remember, the alveolar pressure minus the intrapleural pressure is described as that transpulmonary pressure, that distending pressure, and the change in that transpulmonary pressure is also a variable when we talk about lung compliance. And so a larger compliance, right, which is ideally what we want to see in the lungs, means that it's easier to inspire, and we need a smaller change in transpulmonary pressure to bring the same amount of volume of air in. And another way to say that is thinking about this equation, right? The fact that this change in transpulmonary pressure is inversely related to lung compliance, I can bring more air in more easily with a smaller change in transpulmonary pressure, and that means my lung is more compliant, okay? So a larger change in volume, in other words, more air coming in, for a smaller change in pressure, in other words, less of a change in transpulmonary pressures, and that is a highly compliant lung, okay? And so in another way to express that again is that the lungs don't have to be working as hard to bring that air in because they're just nicely opening up, they're obedient, right? That's another word that we use to describe compliance. And so that is the case with a highly compliant lung. Now, some of the factors that affect compliance are going to be elasticity of the lung. If a lung is more elastic or it has more elastic properties, it's going to be less compliant. And we'll speak about some of the restrictive lung diseases a little bit later on in this packet. But essentially, if the lungs are really rigid, inflexible, they are going to be harder to aerate. It's going to be harder for air to come in because they're going to be acting like arteries. So when you think about elasticity here, think about those large elastic arteries. They're going to generate a lot of pressure for a change in volume, and that's not ideal in terms of air coming into the lung. Another factor that affects compliance is the surface tension within the lungs, specifically within the alveoli. And so surface tension is a force that wants the alveoli to collapse or to resist any expansion. It's caused by a thin layer of water, a thin layer of fluid that lines the inner surface of the alveoli, and that surface tension is due to the interaction between water molecules. So let's kind of illustrate that here to make a little bit more sense here. So let's say we have our alveolus or alveoli. Okay. Now within the alveoli, we have a thin layer of fluid, and we know fluid is usually water here. So we've got water, water, water. Now we talked about this idea that water is polar because of the oxygen on here. And oxygen is a very, oxygen has an uneven sharing of electrons, so it's an electron hog. It wants to be making interactions with other molecules. And so because of this oxygen that has these uneven pairing of electrons, we see this interaction between one molecule and another. So it wants to be making these interactions all across the surface of this alveolus. And so that is what we mean by surface tension. That thin layer of fluid that has water, that is made of oxygen, wants to interact with each other, and so it naturally wants to collapse. And so the greater the tension, the less compliant the lungs are going to be. right? And the greater the surface tension existing within the alveoli, the less compliant, right? The harder it's going to be to keep the lung expanded because the alveoli are going to be trying to collapse upon themselves because of this surface tension. Okay. Now, to overcome the surface tension, what's present inside the lungs is called surfactant. Anyone remember surfactant from our previous discussions? Anyone remember what type of molecule surfactant is? Any ideas? Yes, excellent. Thank you. It's a phospholipid. And so by it being a phospholipid, it is amphipathic. Okay. We talked about it being secreted from the type 2 alveolar cells, and it's going to act as a detergent to decrease or combat that surface tension that we just described. And if you think about the word detergent, it's acting as the same way as any other type of detergent. So dish detergent, soap, skin detergent, laundry detergent. And it's basically breaking up those interactions the same way that we use those types of detergents to remove oil from our clothes, to remove, stains or oil from our dishes, oil from our skin. It's doing that same thing. Because of its amphipathic property, it's got this polar head, this non-polar tail, right? So it's going to be interacting with this oxygen, and then it's going to be extending its non-polar tails to the internal surface of the alveolus in this case. And so this is what we mean by breaking up that surface tension. So the polar head interacts with oxygen or water that's in the surface, and the non-polar tail sticks out to the middle. And so it prevents any kind of shearing or grabbing or attraction from happening and keeps the alveolus nice and open, nice and patent, okay? So the presence of surfactant increases lung compliance and actually makes it easier for inspiration to occur. And just a quick clinical correlation here, surfactant is not created until very late in fetal life. So beyond the 3rd trimester of life is when the lungs start to generate surfactant. And so if we have premature newborns or newborns who are born before term, they typically don't have this on their own. And so they need to be placed on a ventilator to assist them breathing for that additional month or so until their lungs fully develop and until they can secrete their own surfactant to keep their lungs nice and open and patent. Okay, let's look at another example here as far as the alveolus and keeping them open and the presence of surfactant. So this brings into question what's called Laplace's law. So this is Laplace's law. And this basically says that for a given amount of pressure, there is 2 times the surface tension divided by the radius of that container. And in terms of the application in the alveolus, if we look here, this alveolus, which is visibly smaller than this larger alveolus, it's going to have a larger amount of pressure, right? If you think about the inversely proportional relationship here, a smaller radius equals more pressure. So this smaller alveolus 1, has a smaller radius, therefore it has a higher pressure, okay? If we think about alveolus 2, the opposite is true. It has a larger radius, therefore a smaller pressure, right? So we've got a high pressure in alveolus 1 and a low pressure in alveolus 2. And what that creates is a pressure gradient, okay? So we have air wanting to move from an area of high pressure here to an area of low pressure here. And that is not ideal. That's going to cause the collapsing of this alveoli when the air rushes into this one, okay? And so to combat that, what we see is surfactant. So surfactant is breaking up those interactions, and it's also going to equalize the pressure so that we have no pressure gradient. In other words, the amount of pressure existing in this container are in this alveolus is the exact same as the amount of pressure existing in this alveolus because of the presence of surfactant. And so we don't have the collapsing of the smaller alveolus into this larger one because of the difference in pressure. Instead, we have both alveoli nice and open and patent, and they have equal pressures distributed among them. Okay. All right, hope that's clear. So that's kind of one way that we equalize the pressures within different alveoli, although they're obviously very different in their sizes. We also spoke about another structure that helps to equalize the pressures earlier. Does anyone remember what that structure was? So we talked about another structure when we looked at the structure of our alveoli, and it helped to equalize the amount of pressure existing in different alveoli. So someone's asking, does surfactant make for no pressure gradient or equal pressure gradient? So it makes for equal pressure, in other words, no gradient, right? If both of the pressures are the same, there's no high to low or low to high, there's no gradient. So in doing so, it equalizes the pressure in all the alveoli, although they're different sizes. And typically, if they are different sizes, they would normally have different pressures according to Laplace's law. But if we have surfactant present that equalizes those pressures by breaking up those interactions, then we have no gradient and we have no movement of air from that high to low pressure. Okay. All right. So the question I was asking was the structure that is also present among alveoli that helps to bring about this equalizing of pressures. Anyone remember that structure? Okay, so we talked about previously when we looked at the structure of our alveoli that there are these pores. So if you remember, I wish I could go back to that slide, but if you remember us speaking about the alveolar pores, these tiny openings that are found throughout the alveoli, this is another structure that helps with this effect. It's going to equalize the pressure because one alveoli can communicate to another alveolus, and so we can have the equalizing of the pressure, which again is preventing that gradient and preventing smaller alveoli, which have higher pressures, from collapsing into larger alveoli, which have lower pressures.